Hello everyone. Automated program repair techniques have long been a popular area of research. APR techniques aim to repair various software defects in an automated manner to reduce the tedious work of manual repair and improve the repair quality to guarantee software reliability. In recent years, with the popularity of deep learning techniques and the availability of a large amount of bug-fixing data, researchers have started to use data-driven solutions to repair software bugs. By leveraging the powerful learning ability of neural networks and the large-scale corpus, these driven solutions have guaranteed started to surpass previous APR techniques and become a popular technique path. And for security researchers, we prefer to use them for automated vulnerability repair tasks. However, there are still many challenges to the progress of repair research. First, most of the candidate-driven tools are designed for software bug or code error repair, but very little work to explore security vulnerability repair. As a result, we don't yet know the performance of data-driven repair techniques on vulnerability repair tasks. The second issue is multi-line vulnerability repair. Most APR tools are designed for single-line bug fixing. However, previous research have demonstrated that multi-line bugs are more common in real-world environments. Therefore, more efforts on multi-line bugs repair are needed. We hope to explore further and find insights that can help solve multi-line bugs. Besides, data-driven APR tools have limitations in capturing and understanding programming language features in depth. They tend to ignore high-level dependencies such as data flow and control flow. This leads to the possibility that they may generate some incorrect patches. It motivates us to develop our programming language model-based security vulnerability repair approach that leverages pre-trained programming models, codebirds, and graph codebirds to control the downstream task vulnerability repair. These models can work effectively on natural language and programming language downstream tasks and capture rich code semantic features. Besides, the pre-trained models we use have already seen much programming language knowledge in pre-trained phase and can capture the data flow relationships of code. Thus, our approach can better handle programming language features and coverage faster in the downstream task. In short, the contributions of this paper are as follows. This paper proposes a programming language model-based security vulnerability repair approach to overcome the shortcomings of excessive data-driven repair tools for vulnerability repair. We try to use pre-trained programming language models like codebirds and graph codebirds to address the vulnerability repair problem. Besides, we evaluate our approach to different types of vulnerabilities. In addition, we replicated 4 state-of-the-art APR tools for comparison. Final results show that our approach has good repair capability. In our approach design, we use the pre-trained programming language model, codebirds and graph codebirds for the APR tool to work better on the programming language. Further, we also choose graph codebirds with added data flow dependencies to explore the impact of added code dependencies on more complex multi-line bug fixing tasks. Figure 1 describes an overview of our solution, which applies pre-trained programming language models to automate repair vulnerabilities. First, we extract the vulnerability code and the corresponding fix code in the form of the bug fix pairs to serve as train data. Then, we use the pre-trained programming language model to center it on the downstream task of vulnerability repair. Here, an automated module is evaluated for vulnerability repair during the experiments. Finally, an experimental testing phase, we include the vulnerability code to allow the model to generate the predict fix code. For simplicity, we will call these two downstream tasks codebird fix and graphic codebird fix. For the benchmark dataset, the software assurance reference dataset is a suitable choice that satisfies our requirements above. It provides researchers with a set of non-security vulnerabilities for testing and evaluating their tools and methods, and gives simple vulnerabilities for a variety of programming languages. Here, we will evaluate the specific performance of each module and tool on Juliet C. Limited by space, we didn't test hundreds of CWE times of vulnerability data, but select 5 of some for the experiment. The detailed data information is shown in Table 1. Each of these types of vulnerability data contains single-line vulnerabilities and multi-line vulnerabilities. A single-line vulnerability is one that requires only one line or multiple consecutive lines of code to be modified at the time of repair. A multi-line vulnerability is one that requires modification of multiple non-consecutive locations at the time of repair. To compare the performance of each API tool or method, we choose these state-of-the-art API tools: Chengyi, IFIP, SequenceR, and Coconut to evaluate the performance of single-line and multi-line vulnerability repair in comparison with our schemes. In our experiment, we set the above detailed configuration. In fine-tuning phase, we select the model with the highest loss scores as the biased model and use it for the experimental testing. In addition, when we use the other API tools, we kept their original parameters, adjust the size to 5, and increase the input and output length appropriately. In addition, to avoid the impact of localization bias on the experimental results, we use our consistent localization strategy for all API tools or methods. Here, we use the perfect for the localization. Then we mark the defined locations and enter them into the model along with the context content of the defined code. In our experimental results, we show that the number of successfully repaired vulnerabilities as a percentage of the total number of vulnerabilities. We also use repair accuracy to reflect the repair capability of different repair solutions. In the real world, a vulnerability may have multiple effects. Therefore, as long as the predicted repair code pre-generated by the repair tools is in the target site, we consider this pre to be the correct repair. Overall, SequenceR achieved the best result on the single-line vulnerability repair task. The repair performance of our approach is close to that of SequenceR. More importantly, our approach achieved the best results on the multi-line vulnerability repair task. With the above experimental results, the pre-trained programming language models show extended capability on the vulnerability repair task and are ahead of previous work. Next, we analyze the experimental results and point out the strengths and weaknesses of our approach. Its overall size codebird fix and graph codebird fix achieve a leading level on single-line repair, close to SequenceR performance. More importantly, both codebird fix and graph codebird fix have multi-line repair capability, which far surpasses Japan. Among them, graphic codebird fix, which incorporates the flaw information, is closer to codebird fix. in terms of single-line vulnerability repair capability, but has a significant improvement in the effectiveness of multi-line vulnerability repair. This is because single-line vulnerability are generally This because single-line vulnerabilities are generally simpler and don't require the model to deal with overly complex logical relationships. Multi-line vulnerabilities often have complex data dependencies, so the graphic codebase model, which can record rich flow graphics, is more advantaged in handling complex tasks. In summary, pre-trained programming language models have greater potentials for handling vulnerability repair tasks, and recording rich data flow in relationships can help repair more complex vulnerabilities. We have only overused the powerful repair ability, but it's not possible to ignore the shortcomings. We analyzed the examples of repair failures and found two main failure scenarios. First, codebase phase and graph codebase phase are prone to generate files with semantic structure, integrate errors. See figure 4 and 5. In field phase, examples of missing or redundant are often generated. These field examples often generate a correct repair code, but name structure incompleteness is previously correct repair to be the formula. Even though they can encrypt the semantic correctness, they are often still negligent about the semantic structure. Second, codebase phase and graph codebase phase have poor predictive power on the problem of examining wrong code sequence. We observed that many overlines vulnerability code segments generated incorrect repair code. This also injected these pre-trained programming language models are still lacking ability to handle large-scale program code problems, and overly complex codes are often not handled well. We implemented tutorials using pre-trained programming language models for the vulnerability repair task and compared them with some leading API tools. The results show that using pre-trained programming language models can efficiently handle the vulnerability repair task. Our solution is close to the state-of-the-art API tools on the single-line vulnerability repair task and solves the multi-line repair problems that previous API tools struggled to handle. Our results also demonstrate that adding rich code dependencies features will help API tools to address complex multi-line vulnerabilities, which points the way to future work. In addition, our work can sincerely support repair tasks in multiple programming languages. Therefore, we will use multiple benchmarks in multiple programming languages in future work and explore the specific performance of more pre-trained programming language models on vulnerability or bug repair tasks.